Hello everyone, once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. In this video we are going to study about two-dimensional motion or motion in a plane. We'll discuss about position and displacement vectors in two dimensions. We'll discuss two-dimensional motion with uniform velocity, uniform acceleration. So we pick up with motion in a plane. Here motion in a plane or two-dimensional motion is treated as vector sum of two one-dimensional motions in two mutually perpendicular directions. So what does this statement say? That two-dimensional motion is always a vector sum of two one-dimensional motions in two mutually perpendicular directions. So let us discuss about position and displacement vectors in two dimension. Here we consider a particle moving in XOY plane. So this represents the XOY plane. The particle is being made to move from point P1 to P2. The point P1 is described by the position vector R1, and similarly the point P2 is described by the position vector R2. Now what are position vectors? The vectors which describe the positions of the point in space with respect to the origin are called as position vectors. The coordinates of the point P1 are x1, y1, and similarly for the point P2 are x2, y2. Delta R represents displacement from point P1 to point P2. So let us consider a particle moving in XOY plane from the point P1, that is x1, y1, to the point P2 with coordinates x2 and y2. The vector OP1 would be equal to R1 and the vector OP2 is equal to R2. What do? They define the position vectors for the points P1 and P2 respectively. R1 vector can be written as I of x1 plus j of y1. Similarly, R2 can be written as I of x2 plus j of y2. Here I cap and j cap are unit vectors along x and y directions respectively. The vector P1 P2 is equal to delta R gives the displacement of the moving particle during the time interval t to t plus t delta t. So P1 is the position at the time t, P2 would be the position at the time t plus delta t. So it performs a displacement delta R in the time interval delta t. We are going to use the triangle law, and according to the triangle law, OP1 vector plus P1 P2 vector must be equal to OP2 vector. So we can find P1 P2 vector can be written as OP2 minus OP1. So delta R can be written as R2 minus R1. R2 vector I of x2 plus j of y2, and R1 vector I of x1 plus j of y1. x2 minus x1 I cap plus y2 minus y1 j cap. x2 minus x1 can be written as delta x. Similarly, y2 minus y1 can be written as delta y. And in vector form can be written as delta x vector plus delta y vector. We call this as equation number 1. What are delta x and delta y? Delta x and delta y are the two rectangular components of the vector delta r. What is the magnitude of delta r? It would be under root of delta x chi square plus delta y chi square. So what does the equation number tell me? 1. The two-dimensional displacement delta r is equal to vector sum of two one-dimensional displacements, that is delta x and delta y, in two mutually perpendicular directions. So the general statement for displacement has been proved, that two-dimensional displacement is nothing but vector sum of two one-dimensional displacements in two mutually perpendicular directions. Now let us talk about two-dimensional motion with uniform velocity. The velocity of a particle is said to be uniform if it covers equal displacements in equal intervals of time, howsoever small these intervals may be. So when is the velocity said to be uniform? When the object covers equal displacements in equal intervals of time. Whatever smallness be the smallness of time intervals. Here we like to define average velocity and instantaneous velocity. Average velocity is the ratio of displacement and the corresponding time interval. So average velocity v bar is equal to delta r by delta t. Delta r could be written as I of delta x plus j of delta y upon delta t. Can also be written as I cap delta x by delta t plus j cap delta y by delta t. Delta x by delta t can be written as vx and delta y by delta t as the y component of average velocity. So we write it as vy. So according to equation 2, v bar can be written as I of vx bar plus j of vy bar. The direction of the average velocity is along the direction of displacement vector. So average velocity का वही direction होगा जो displacement vector का होगा. Now we come to instantaneous velocity. Here we will try to understand what is limiting value delta t tending to 0 mean for us. The instantaneous velocity is given by the limiting value of average velocity as the time interval approaches 0. So v can be written as limit delta t tending to 0 delta r by delta t is equal to dr by dt. Here average velocity is along the direction of displacement in all the figures. We are moving first from the point P to P1 in the time interval delta t1. We are moving from point P to P2 in the time interval delta t2, and we are moving from point P to P3 in the time interval delta t3. And remember, delta t1 is greater than delta t2 and is greater than delta t3. That means as we are moving from figure A to B to C, the time interval delta t is continuously reducing. What does this figure do? This figure explains the limiting process. The thick lines in the figure represent the path of an object which is at the point P at the time t. P1, P2 and P3 represent the positions of the object after the time delta t1, delta t2 and delta t3. So this is the point P1, this is point P2 and this is point P3. Here it is delta R1, delta R2 and delta R3. So remember, delta R1, delta R2 and delta R3 are displacement of the objects in the time delta t1, delta t2 and delta t3. The direction of the average velocity is shown in the figure. A, B and C for decreasing values of delta t. As delta t tends to 0, delta r also tends to 0 and is along the tangent to the path. The direction of the velocity at any point, so just look at the figure once again. As delta t tends to 0, just see the direction of the velocity is along the direction of displacement. So that is what we have written here. The direction of velocity at any point on the path of an object is tangential to the path at that point and is in the direction of motion. So we can express v in component form. V would be equal to dr by dt, limit delta t tending to 0, I of delta x by delta t plus j of delta y by delta t. Now just we can write it as this way also. I cap limit delta t tending to 0, delta x by delta t plus j cap limit delta t tending to 0, delta y by delta t. Or v can be written as I of dx by dt plus j of dy by dt can be written as I of vx plus j of vy. So vx and vy are the x and the y component of instantaneous velocity. The magnitude of v would be given by under root of vx ka square plus vy ka square. Now how do we calculate the direction of the velocity? So the direction of the velocity is given by the equation tangent theta is equal to vy by vx. So this represents the angle theta here. And tangent theta would be equal to perpendicular upon base, so vy upon vx. Here vx, vy and angle theta are shown in the figure for a velocity v vector at the point P. Now what do the equation number 2 and 3 tell me? They tell me that two-dimensional velocity is nothing but equal to the vector sum of two one-dimensional velocities in two mutually perpendicular directions. Now let us discuss acceleration. We'll talk about instantaneous acceleration, we'll talk about average acceleration. The average acceleration of an object for a time delta t moving in the xy plane is the change in the velocity divided by time interval. So average acceleration, change in velocity to time interval, and v can be written as I of vx plus j of vy. So can be written as I of delta vx by delta t plus j of delta vy by delta t. This represents the x component of the acceleration and this would represent the y component of the acceleration. So average acceleration would be I of ax bar plus j of ay bar, and we call this as equation number 4. Instantaneous acceleration is nothing but the limiting value of average acceleration as the time interval approaches 0. Limiting value of average acceleration as the time interval approaches 0. So instantaneous acceleration is limit delta t tending to 0 delta v by delta t. Since delta v is I of delta vx plus j of delta vy, so I get I of limit delta t tending to 0 delta vx by delta t, limit delta t tending to 0 delta v by delta t can be written as I of ax plus j of ay. This represents the x component of the instantaneous acceleration and this represents the y component of the instantaneous acceleration, giving me equation number 5. What do equation number 4 and 5 tell me? They tell me two-dimensional acceleration is equal to the vector sum of two one-dimensional accelerations in two mutually perpendicular directions. So the general statement is correct. In two-dimensional motion, either two-dimensional displacement, two-dimensional velocity or two-dimensional acceleration is nothing but vector sum of two one-dimensional components of either displacement, velocities or accelerations in two mutually perpendicular directions. We have put up a note here for you all. In one dimension, the velocity and acceleration of an object are always along the same straight line, either in the same direction or in opposite direction. For motion in 2 or 3 dimension, the velocity and acceleration vectors may have any angle between 0 to 180 between them. Now, let us talk about principle of independence of directions. So, according to principle of independence of direction, the motion along two mutually perpendicular directions are independent of each other. That means motion along x is independent of motion along y. Similarly, motion along y would be independent of motion along x. Now let us talk about motion in a plane with constant acceleration. Now, when is the body said to have uniform acceleration? When it has a velocity changing by equal amounts in equal intervals of time. So we have written a body is said to have uniform acceleration if the velocity changes by equal amounts in equal intervals of time. By definition, acceleration A can be written as change in velocity to change in time, v minus u upon t minus 0. What is v? The initial velocity at the time, what is u? Initial velocity at the time t is equal to 0, and at the t is equal to t time, the final velocity is v. So rearranging the terms, I get v vector is equal to u plus at, called as equation number 1. We can express the various quantities in form of components. The initial velocity can be written as u is I of ux plus j of uy. Final velocity can be written as I of vx plus j of vy. Similarly, acceleration can be written as I of ax plus j of ay. Substitute these three in the equation number 1. So I of vx plus j of vy would be equal to I of ux plus j of uy plus I of ax plus j of ay into t. Here x and y directions are mutually independent, so you can compare the coefficients of I cap and j cap on both sides. Comparing the coefficient of I cap, I get Vx is equal to Ux plus Ax into t, and comparing the coefficients of j cap, I get Vy would be equal to Uy plus Ay into t. What do these two equations tell me? The two equations show that the two rectangular components of velocity for an object moving with a uniform acceleration depend on time as in one dimensional accelerated motion. जैसे वन डायमेंशन एक्सेलरेटेड मोशन के अंदर यूनिफॉर्म एक्सेलरेशन टाइम पर डिपेंड करता था, सेम वे यहां पर भी एक्स एंड वाई कंपोनेंट डिपेंड ऑन द टाइम सेम वे. नाउ वी विल फाइंड हाउ डज पोजीशन वेक्टर r change with the time. Let r0 and r be the position vectors of the particle at the time 0 and t respectively, and let the velocities be v0 and v. So v0 is the velocity at the time t is equal to 0, r0 is the position at the time t is equal to 0, v is the velocity at the time t, and r is the position at the time t. The average velocity in time interval t is given by v0 plus v upon 2. How do we calculate displacement? So displacement would be given by average velocity into time interval. So r minus r0 is equal to v plus v0 upon 2, that is average velocity into time. Now v can be written as v0 plus at. So what do I get? R minus r0 would be v0t plus half at square. So position r can be written as r0 plus v0t plus half at square. So what does equation number 2 tell me? It tells me what will be the position of an object moving with a uniform acceleration after time t. The derivative of this equation dr by dt will give equation 1. So writing equation number 2 in component form, we get I of x plus j of y is equal to I of x0 plus j of y0 plus I of v0x plus j of v0y into t plus half I of ax plus j of ay into t square. So comparing the coefficients of I cap, what do I get? X would be equal to x0 plus v0x into t plus half ax into t square. Similarly, compare the coefficients of j cap. So y would be equal to y0 plus v0y into t plus half ay into t square. This shows that motion along x and y directions can be treated independently of each other. So motion in two dimension can be treated as two separate simultaneous one-dimensional motions with constant acceleration along two mutually perpendicular directions. So let us pick up certain examples to understand what we have done. The position of a particle is given by r vector is equal to 3.0 t I cap plus 2.0 t square j cap plus 5.0 k cap meter. Find the velocity and acceleration of the particle. Find the magnitude and direction of velocity at the time t is equal to 1 second. So if I need velocity, I must differentiate the position. So dr by dt would be d by dt of this equation. So differentiating, I get 3 I cap plus 4 t j cap. Once again differentiate velocity to obtain acceleration. So acceleration would be dv by dt. So d by dt of 3 I cap plus 4 t j cap. So I get 4 j cap. That is 4 meter per second square in y direction. At the time t is equal to 1 second, the velocity would be given by 3 I cap plus 4 j cap. So velocity would be under root of 3 chi square plus 4 chi square, that is 5 meter per second. And the direction would be given by tangent inverse Vy by Vx. That is tangent inverse 4 by 3, that is an angle of 53 degree with x-axis. So if I know the position, I can calculate velocity and time by the method of differentiation. A boat has another example here. A boat has initial coordinates x1, y1 given by 100 and 200 meter. 2 minutes later, the coordinates are x2, y2 and they are 120 meter and 210 meter. What are the components, magnitude and direction of average velocity for this 2 minute interval? So x1 is given, x2 is given, y1 is given, y2 is given. I can calculate delta x and delta y. And the time given is 2 minutes. So I can calculate component of average velocities. Vx would be delta x by delta t, will be 20 upon 2, that is 10 meter per minute. Vy would be equal to 10 upon 2, that is 5 meter per minute. Now, velocity makes an angle theta with the x-axis. So tangent theta would be Vy by Vx. So tangent theta would be 5 by 10, that is 0.5. So angle would be 26.6 degree with respect to the x-axis. Another example let us pick up. An aircraft is flying at a height of 3400 meter above the ground. If the angle subtended at a ground observation point by the aircraft positions 10 seconds apart is 30 degree, what is the speed of the aircraft? So A and B are the two aircraft positions which are 10 seconds apart, A and B. From the figure I can calculate tangent 15. It would be AC upon CO. So AC upon, and the distance is 3400 meter. So I can calculate AC, it would be 3400 tangent 15. The value of tangent 15 is 0.2679. So I get AC as 910.86 meter. Now, speed of the aircraft is 910.86, that is the distance AC upon the time, that is 5. So 182.2 meter per second. So hope that the earlier videos have been useful for you. मेरा आप सभी से रिक्वेस्ट है कि हमारे चैनल को सब्सक्राइब करें, बेल आइकन बटन को प्रेस करें ताकि अगला वीडियो का नोटिफिकेशन आपको सही टाइम पर मिल सके. वीडियोस पर लाइक करें और कमेंट करें. थैंक यू वेरी मच.